Here we'll go through each of the practice problems for Unit 1, just reviewing what we already know about R from BAS 320, using R as a calculator referring to vector elements, doing basic calculations, that kind of stuff. So the first thing that you're asked to do is to translate some mathematical expressions into R. Now, the way that mathematical expressions are written in an RMD file look rather funny, so I'm going to go ahead and just knit to HTML so that I can see what these equations look like, so I can do that translation a bit more efficiently. All right, so part A wants us to take the fraction x squared over x minus 1 and show it's equal to minus 0.5. We're supposed to left arrow x to be 1/2 first. So let's go ahead and left arrow x to be 1/2 so that x assumes the definition of 0.5 in the global environment. We can see it show up here. And to write this, we just need to remind ourselves that to raise something to a power, we use the caret symbol. And because I have the quantity x minus 1 in the denominator, when I divide, I want to make sure to add some parentheses to capture that the x minus 1 has to happen first before we do that division. So define x as 1/2, x squared over x minus 1, and indeed it's minus 1/2. All right, next equation. This is something that we would see in logistic regression, trying to predict the probability of something happening. In order to take e and raise it to some power, we need to use the R function exp. And in parentheses, we're going to put what we're raising. So in this case, minus 0.7 plus 1.2 times x. And once again, when we divide, because we have an expression in the denominator, we need to make sure to put parentheses 1 plus exp raised to the minus 0.7 plus 1.2 times x. And we get out what we expect, so that looks good. Equation number 3, the log base 10 of the absolute value of the natural log of x. Well, here's the thing to remember is that log 10 is log 10 in R. The absolute value function is just ABS. And natural log, R refers to as actually just log, without any sort of subscript or any other addition. We see that we get that correct as well. All right, moving out to part D, we have 0.5 times 9 minus 3 plus 3 squared times 6 over 2x plus 3. So we have to remember about the implicit multiplication symbol. If we're multiplying 0.5 times the quantity 9 minus 3, we might write it like this, but we need to make sure to actually tell R to put that multiplication symbol between that 0.5 and the thing in parentheses. All right, plus 3 squared times the quantity 6 divided by, and once again we see an expression in the denominator, so we want to make sure to have those parentheses. And we get that it's 16.5 as expected. Next question, we need to make sure to include those parentheses again. 3x is 3 times x, making sure we have that, times x minus 5 plus 2 times x raised to the 4th power. Yep. Number 6, because we have an expression in the numerator now, we want to make sure to have parentheses around that expression. 5 minus 2 times e raised to the minus x over 2 power, making sure to have that implicit multiplication symbol between the 2 and the e. And then divided by, once again, an expression, so parentheses 5 plus the square root of the log of x, natural log, plus 9. So here we see the natural log of x plus 9. So here we omit parentheses so that we don't accidentally treat x plus 9 together. And when we run that, we get a slightly different answer than what we had expected. So let's go and double check, because I wonder if I had intended originally to have log x plus 9. Let's close out those parentheses. Aha. So it looks like I have a very small typo. I actually did want the parentheses around the x plus 9. And I'm going to add that to this document just to have that clear. And I'll go back and fix the original. All right, G, we have an expression in the numerator. So parentheses x plus 7 over 3 times the log base 10 of the quantity 0.5 times x squared minus x over 3 plus 1. remembering that implicit multiplication symbol, the 0.5 times x squared. That's confirmed. And then the quantity 1 plus 2 times x squared, all of that raised up to the 4/3 power. Key thing is because we have an expression in the exponent, we need to make sure that that expression has parentheses around it so that it gets computed correctly. All right, the next question asks us to create a vector called BAS474 that's some sort of big sequence here. Looking at just the first few elements, here's what the sequence looks like, and we're asked for a few properties of this sequence. So we'd like to know what fraction of elements, so in this case we have a sequence of length 1000, so what fraction of them, 0.1, 0.8, etc., fraction's always a number between 0 and 1, are less than 5. Now, to answer questions like this, we'll use our logical operators. So if I say BAS474 less than 5, and just run that as a command, I'm going to get a whole bunch of trues and falses out. So false when that expression is false, and true when the expression is true. So to figure out the fraction that are less than 5, what I'd like to know is, okay, well, what fraction of these elements are true? And there's a nice way to do this. False is the number 0 in R, and true is treated as the number 1. So if I ask for the mean of this vector, I get that 77.3% of those elements are less than 5. What's another way of doing that? Well, I could brute force count up the number of elements that are less than 5 with the combination of length and which. If you remember that the which command, when we pass something to a function, it reports back the positions inside the vector that meet our logical condition. So which BAS474 less than 5 goes through the vector BAS474 and reports back that the 228th element is less than 5, the 230th element is less than 5, etc. And we just want to count up the total number of elements in that vector. Length gets us there. And so we see that in total we have 773 elements that meet this condition. And to convert that into a fraction, I just need to divide by the number of elements that we were dealing with. So length, which BAS474 less than 5 divided by length of BAS474 gives me the fraction of elements. We get that 0.773, and you can see why I prefer just using mean here. So I'm going to continue to use mean to answer these other questions. What fraction are between 1 and 2, including those numbers? Well, let's write out that logical condition. It would be nice to write out something like this. I'm going to write this out incorrectly, just to show you that I can't do this. This is how we would write this if we were just writing it on a piece of paper, doing math on paper here. If I try to run this, I get an error. It says unexpected less than or equal to. And that's because R can only handle one expression at once, one logical condition at a time. So if I want to ask if something's between 1 and 2, I actually have to ask two conditions separated by the ampersand. That's how we put more than one condition in our expression. So what we really want is BAS474 being at least 1 and BAS474 being at most 2. So to capture between a certain range of values, I actually have to write two logical expressions, one using less than, or one using greater than, and one using less than. So BAS474 less than or equal to 2, BAS474 greater than or equal to 1. This will report back trues and falses. If I ask for the average, I'll get that 7.2% of those values are between 1 and 2. So we had less than 5, we had between 1 and 2. All right, what fraction are integers? Well, that's an interesting question. What we basically want to know is we want to know, do we have any 1s? Do we have any 2s, 3s, 4s, 5s, 6, etc.? In this case, because integers is a large number of values, we can use the percentage in shortcut to quickly determine, all right, what elements in BAS474 are also in a vector containing integers. So what I'm going to do is I'm actually going to look at a summary of BAS474 first of all to know what kind of integers I'm talking about. So it's saying that the smallest is 0, the largest is 2, 6, 4, 5. So what I'm going to do is to create the integer sequence 0 up to 2646. Now, we might actually have some numbers beyond this decimal place here. So just to make sure that I have all integers inside this range, I'll go from the very smallest, 0, to a little bit larger than the biggest number that I see, kind of rounding up to the nearest integer. So here are all the integers I want to look for. And I want to know, okay, well, what fraction of the elements in BAS 474 are exact integers? Might not be any at all, in fact, I'm not exactly sure. So what we can do is use the percentage in shortcut. If I ask BAS 474 percentage in the integer sequence 0 to 2646, what it will do is dive inside the BAS 474 vector and one by one go through each element and check to see, all right, is it somewhere inside this vector, this integer sequence? If so, it returns a true. If not, it returns a false. So if I run the command, I see a whole bunch of falses. All those elements were not integers. And in fact, I might not see any trues at all. Now, it's hard for me to really tell just by scanning through here. So if I ask for the average value of this true-false vector, I actually get back a 0. There are no integers in this sequence, in fact. All right, next question, less than 1 or greater than 5. So again, this is two conditions, so I'm going to have to write these two conditions separately. Being less than 1 would be BAS 474 less than 1. Greater than 5 would be BAS 474 greater than 5 here. How do I get this OR to be represented? Well, I'm going to use the pipe symbol. Shift backslash here, and this is how R treats OR. So BAS 474 less than 1 or greater than 5. I see a bunch of trues, some falses. I can ask for the mean of this logical vector to get the fraction of elements that meet these one of these two logical conditions. And then finally, wow, we're asking for a lot of stuff here. Less than 2 or between 4 and 5 or greater than 7. And here's where some parentheses are going to come into play. Because there's so many expressions going on, it's a good idea if I use parentheses just to make sure that R treats conditions together when it should be. What do I mean by that? Well, I know that between 4 and 5 requires two expressions to capture, so I should probably write some parentheses around them just to make sure that it's being processed correctly. All right, so I have a bunch of ORs here, so less than 2 would be BAS 474 less than 2, or then I'm going to put in my parentheses and do the between 4 and 5. So to be between 4 and 5, we need to have 4 be less than BAS 474 and BAS 474 be less than 5. So BAS 474 is between the range 4 and 5. Close out the parentheses here so we make sure that this expression is being evaluated as between 4 and 5. And then another greater than 7, so BAS 474 larger than 7. If I just run that, lots of trues, some falses, and I can get the average of this vector to get the fraction of elements that meet that condition, so about 88.6%. All right, part 0C asks us to run the following line of code, and it generates a data frame. We see that in the environment now, with 5,000 rows, 4 columns. Here our columns are x1, x2, y1, y2, and we're being asked to use subset to define subsets that meet the following criteria. And figure out the number of rows in each of the subsets. And we're given the answers so we can make sure that, hey, we got this correct here. All right, so we want a subset where x1 is at least 8. So I'm going to go ahead and just left arrow into a data frame called sub, the result of running subset on BAS. And what do I want to be taking a subset of? Well, rows where I have x1 being at least 8. At least is greater than or equal to, and there we go. So how do I get the number of rows? Well, n row of sub will tell me this. So indeed, 1368. Part B, y1 is the letter A. All right, well, take a subset of BAS. And in this case, we want to see if y1 is equal to A. Now, two things here. In order to check equality, I actually need a double equal sign. Single equal sign sets equality, the equivalent of the left arrow here. And if I'm going to check to see if it's a letter A is a letter, it's text, so I need to make sure that it's in quotes. So I can run that subset, and I can see, yep, 192 rows here. Part C, Y2 are the letters B, A, or S. Well, there's a few ways to go about doing this. I'll show you my favorite way first. We'll use the subset command once again. And what's our condition? We want to make sure that the columns are equal to one of B, A, or S. And so this is a good chance to use %in here. If I use %in, what we'll do is we'll go through this column and we'll just get the elements that appear in the vector that we put to the right-hand side of %in. So I could say B, A, S, all text and all in quotes. And I would get my subset. So we can see how many there are, 562. Now, what's another way to do this? Well, if I'd forgotten about that %in, I could always just write a whole bunch of ors. I could say Y2 is equal to B, or Y2 is equal to A, double equal signs all around, or Y2 is equal to S. I prefer the %in because then we can put in a really long vector. It requires a lot less typing than specifying it one by one with the ors. All right, D, x2 is between 9 and 9.5. Okay, once again, to check to see if something is in a range, I'm going to need two logical conditions. I need to write this as x2 being bigger than 9 and x2 being less than 9.5. And if I look at the end row of that subset, 624 is expected. X1 larger than X2. Okay, well that condition is easy to write. I just need that the value in X1 is bigger than the value in X2 here. And 341, Y1 is the same as Y2. Well, in the same vein, my conditions can refer to two columns, Y1 equaling to Y2, the double equals because I'm checking equality. 183, X2 is missing. Well, here's a key thing to remember is I can't say, all right, X2 is equal to NA. So NA is R's representation of a missing value, but I can't actually use the double equal sign to check equality. R just doesn't let you do that. So if I try to actually run this, I would end up getting the wrong answer. I'd get 0. So what do I need to do to check to see if something is missing? And just to confirm that's not the right answer. If I run summary of BAS, the X2 column here, I see that there's 65 NAs. So that's clearly the wrong way to do it. Instead, my condition on the rows is I want to have is.NA on X2 evaluating to true. So if I want to check, all right, subset of the rows just where X2 is missing, I need my condition on the rows to be is.NA of X2. And so this will print out 65, so we're good to go. All right, part H, X2 is not missing, and Y2 is one of the first 5 letters of the alphabet. All right, so a few conditions here. So taking a subset of BAS, let's tackle the first. X2 not being missing, it's almost like is.NA, but I want the opposite of that. Is.NA means missing, not with the exclamation point, means that it's present, that it's not missing. So X2 is not missing, and Y2 is one of the first 5 letters of the alphabet. So I could write this as a whole bunch of ors like I did up here, or I could use my favorite, the %in. And in this case, since letters is a vector that R knows about, I don't actually have to type out A, B, C, D all by myself. I can just actually reference that letters vector that R knows about. The first 5 letters would be letters 1:5, and there we go. 946, as expected. Next one, X1 is less than 5. X1 is less than 5, or that's our vertical pipe symbol. X2 is greater than 10. Okay, I didn't seem that bad. $14.30. Let's make sure that we did that correct. I might have messed up with that $14.30. X1 is less than 5, or X2 is greater than 10. Well, that looks pretty reasonable to me, so I feel like I'm going to change up that answer here. And then J. X1 is between 4 and 9, X2 is missing, and Y1 and Y2 are the same. All right, so a bunch of conditions once again. So subset BAS, X1 being between X4 and 9 requires two conditions whenever X1 is in a range, so bigger than 4 and less than 9. And we want X2 missing, so and is.nax2, and Y1 and Y2 are the same, so separating them by double equals. And we get just 2. Let's actually just print out what those two are. There we go. All right, so let's load in the mtcars dataset, which is one of those that R knows about. So we can just load it in with the data command here. And there's a few additional commands to get us acquainted with this data frame. So the output of dim tells us the number of rows and columns, and row and col will do the same, and head, comma 3 will show us the first 3 rows. All right, so we're just about to get started working with this data frame, but first it wants us to create a vector whose 45 elements are this particular set of numbers. So we know that to make a vector we use the C command, and inside those parentheses we just put in the elements of that vector separated by commas. Now in this case, since we want those first elements to be that integer sequence 1 through 10, there's a shortcut. So 1:10 is that integer sequence 1 through 10. And when I make vectors, I'm perfectly allowed to put inside the arguments of C vectors themselves. So I can do 1:10, 12:15, and 20:45 to get the desired sequence. Now we're supposed to verify that there's 45 elements, so we can look at the length of this vector, and indeed there's 45. All right. Part 2 wants us to left arrow into X the values inside the MPG column of mtcars. Now, how do I get just the numbers out of a particular column of a data frame? Well, I say what the name of the data frame is, and then I turn on the $sign. The $sign gives me a column reference, and in fact, RStudio will pop up a list of all the columns that are in that data frame, and I can select it either with my mouse, or if I just want to type it out, MPG, that's what I want. So mtcars $MPG gives me the vector of miles per gallon for each of these cars, and I'll left arrow that into X. Okay, 2a asks us to verify that X is a numeric vector by running the class function, and indeed it's numeric here. We'll produce a 5-number summary to learn a little bit more about the values inside X, the minimum, the maximum, median, mean, and 75th and 25th percentiles here. We can get the first 10 elements of X by using head with the second argument 10. And the last part wants us to find the ratio of the biggest value of X to the smallest value of X. So we can do arithmetic with max and min. We can just take the max of X divided by the min of X to get that ratio. 2b asks us to print out the 2nd, 17th, 18th, and 28th elements of X. Okay, well, no problem. To refer to particular elements of a vector, we turn on the square brackets and then put in a vector of positions that we want to see. So we can make a vector of the sequence 2, 18, or 2, 17, 18, 28, put that inside those square brackets, and that'll print to the screen the elements in those positions. And then we can use that to do additional operations. We want to find the average of those values, so we can just simply take the mean of X square bracket those particular elements. 2c asks us to find in what positions inside X we find elements that are greater than 20, between 12.1, etc. So what we want to do is we want to be using the which command, because the which command tells us where inside a vector we find elements that meet certain conditions. So if I say which X greater than 20, it'll dive inside the vector X and it'll report back, the third element is, the 20th element is, the 80th element. Those are the ones that are bigger than 20. In this case, we find the first, second, third, fourth, and eighth. Just to confirm that this works, all right, yep, that's bigger than 20, bigger, 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 then smaller. And so we see that the fifth element's not bigger than 20 and 5 is omitted from that list. All right, positions between 12 and 20. Well, we know that when we deal with a range, we actually need two logical conditions. We need x to be bigger than 12 here, and we need x being less than 19. Now, my hashtag comment here says between 12 and 19. The original problem says between 12.1 and 19.6, so let's go ahead and do that officially. It looks like elements 5, 6, 7, 10, etc. are. All right, we also want to know how many elements are less than the average value of x. Okay, well, how do we go about doing that? Well, we can get the average value out just by asking for the mean. And so we could say, all right, well, tell me which elements of x are less than the mean. So we have the 5th, the 6th, the 7th, the 10th elements are less than x, or less than the mean of x here. And if I wanted to know what the total number of those were, I could count them up with the length command. Kind of put the result of running that inside the length function, 18 total elements. And if I divide that by the length of my vector here, that'll give me the fraction of elements that are less than the average. So number of elements less than the average of x, that's length which, dividing by the length of x gives me the fraction of elements that are less than the average. I'm just being asked for how many elements total are less than the average, so I'll leave it as that. All right, how many times does the number 21.4 appear in x? All right, well, I could ask which elements of x are equal to 21.4. Double equal sign, because I'm checking equality. Single equal sign sets equality, like the left-hand arrow symbol. And it looks like there's 2 from just printing that out to the screen, but if I do length and width, that'll count up the number of elements that meet that condition, so there's 2. And then finally, what fraction of elements, number between 0 and 1, are less than or equal to 19.2? All right, so let me write that out too. What fraction are less than or equal to 19.2? All right, so if I say which x is less than or equal to 19.2, tells me all these elements are, so I could count up those. 17 total divided by the length of my vector, that turns that into the fraction, so a little over 50%. Now that's one way of doing it, counting up the number of elements that meet that condition and dividing by the total number of elements. I personally like using the mean function because what the mean function does is it takes the average of a vector of values. And the cool thing about R is that if I just run the command x less than or equal to 19.2 by itself, I get a vector of trues and falses. True for if it is at most 19.2 and false otherwise. Now we can do arithmetic with true and false because R treats false as the number 0 and true as the number 1. So if I ask for the mean of this vector, I'm asking for a mean of 0s and 1s, and I get the same answer out. A little bit less verbose than the length which method. Either one really, you can feel free to choose from, but I like using the mean. All right, 2D, the smallest and largest values of x are 10.4 and 33.9. Is that right? Well, yeah, it looks good. How many elements of x are integers? Print to the screen the integer values of x. All right, well, the integers that x could possibly be are going to be somewhere between 11 and 33. So 11 is the first integer it could be, and 33 is the last. So we want to know, do we have any of these values inside x? Well, that's where the percentage in shortcut comes in. If I ask x percentage in 11:33, that'll dive inside the vector x, and it'll report true if that element is somewhere in this vector, whatever vector I give to the right-hand side of the percentage in, and false otherwise. So if I print out my x and I ask x percentage in 11 through 13, we do see that, okay, both these 21s are integers, that returns true. 21.8, that's not, that returns false. Okay, well, one thing I could do is I could say, well, what's the sum of the elements in this vector? Since R treats true as the number 1 and false as the number 0, if I take the sum of this vector, that'll give me the total number of elements that are integers. So sum works, also length which works, same sort of thing. Length which x percentage in 11:33 counts up the number of elements of x that are somewhere inside the sequence. Same sort of thing. Now, print to the screen those integer values. I basically want to print out the elements of x where I do find those integers. So basically, if I ask which x percentage in 11:13, I want that first, second, 27th, and 31st elements. All right, well, that's a vector of numbers. I know how to refer to the positions of a vector. I just type in the name of that vector and then in square brackets put in a vector of those values. So x square bracket, which x percentage in 11:13, will print out the positions from 1 to 27 and 31, which gives me the numbers 21, 21, 26, and 15. Those are the integer values of the MPG in this data frame. All right, 2E wants us to add a new column to MT-CARS called KMPL that contains the fuel efficiency, but in kilometers per liter. So how do we add a new column? Well, we just say the name of the data frame, put a $ to give column reference, and since KMPL doesn't exist here, we're defining it kind of brand new, we just simply type out the name that we want to give the column, and then left arrow that to be the values that we want it to be here. So in this case, we basically want to take the values in the MPG column, multiply that by 0.425, and that's going to give me the fuel efficiency in kilometers per liter. So how do I get the miles per gallon out? Well, $MPG, we'll multiply that by 0.425. Now we've added that column. Notice it appears at the end here, and we want the median value of this. So we want the median value of the KMPL column here, 8.16. And then finally, 2F, print to the screen the value in the 8th row and 2nd column of this data frame. Print to the screen the value in the 17th position of the DRAT column. All right, well, how do we refer to specific positions inside of a data frame? Well, same thing with a vector. We need square brackets, but in this case, because a data frame has 2 dimensions, we need 2 numbers. We put a comma inside those square brackets. The number or numbers to the left of the comma talk about what rows we want to see. The number or numbers to the right of the comma tell us about the columns that we want to see. So in this case, just a single row and a single column. I'll put an 8 to the left of the comma and a 2 to the right of the comma. 8th row, 2nd column, there's my number. Print to the screen the value in the 17th position of the DRAT column. Well, we're asked for the 17th row of the DRAT column. What column number is DRAT? Well, I don't know. So in this case, there's actually an easier way to refer to this. If I do MT-CARS $DRAT, that'll just look at the values inside the DRAT column, and I can just use square brackets there to get the 17th position. Now, since the values in the column is just a vector, I don't need to put a comma here. A vector is a one-dimensional object here, so bracket 17 will put out that 17th position. One other way that you should know about, I can use those square brackets with the comma, and instead of referring to, say, 2 as the column that I want to be referring to, I can actually put in quotes what the column name is. So MT-CARS 17, DRAT in quotes says that, okay, look at the DRAT column in the 17th row up there. All right, part 2 wants us to work with factors in a data frame. And if we look at the MT-CARS data, we see that, all right, things are being encoded numerically when really they should be encoded as levels of a categorical variable. So what we want to do is we want to define VS and AM not to be a bunch of zeros and ones, numerical values, but we actually want them to be categorical variables. So what we're going to do is kind of verify that right now they're both numeric, and we're going to use the factor function to convert these columns into categorical variables, convert the values into a factor. All right, so to change something into a factor, not all that bad, we just use the factor function. Right now, we're going to take the values in the VS column, these are the zeros and ones that we want to make a factor, and just say factor. Inside those parentheses, we put in the values we want to be changing into a factor. If I just run this part of the command, we see that, okay, still zeros and ones, but we get that levels vector associated with it, letting us know that, yep, we're going to be treating this as a categorical variable. So we're overriding the values in VS with their categorical equivalents, and we see that the data frame has changed its definition in the environment. And then same thing with the AM column. We'll go ahead and overwrite the values in there. We see it's become a categorical variable. And because 0 and 1 really aren't that informative names, we're going to rename those levels so that 0 is no and 1 is yes. So one way to rename these levels is to take a look at what the levels vector is. Right now 0 is first, 1 is second, and R allows me to manually just rename those levels by giving it a vector of new names. So my old names are 0 and 1. I can give it a vector of new names, just putting in quotes what I want those new names to be. So in this case, 0 is supposed to represent no, and 1 is supposed to represent yes. So I can run this as is. Take the levels of the VS column of empty cars and rename those levels no and yes. 0, no, 1, and yes. So we see that that is now updated here. And then we can do the same thing for the AM column. All right, now once we have that, we're going to run table. So we get a contingency table of how often we see each combination of values. So the first argument here, VS, VS no, VS yes, that's going to be the row labels. It doesn't actually tell us, unfortunately, but that's what it refers to. And the columns, those refer to the second argument. So this is AM no and AM yes. So we see we get a pretty good mix of each of those four combinations that's possible. All right, now after we've done number 3, we've done this, we're going to use subset to create a subset of cars who have yes for both VS and AM. We're going to call the result sub. Okay, so let's left arrow into sub. The result of running subset on empty cars. What rows do I want? Well, I want the rows where both VS and AM are equal to yes. How do I do that? Well, I can type out the condition on the VS column by saying VS double equals yes. Double equal because we're checking equality. We're not setting equality here. We're selecting the ones that do equal yes. And then how do we get it so that we also are getting the ones where AM is equal to yes? Well, two conditions. We separate them with the ampersand sign. So AM double equals yes as well. So we run it. We can double check our work. We take a summary. We look at VS and AM and we see that, aha, yes, is the only level that appears in our subset. All right, so how many cars meet this condition? That's going to be the number of rows in the subset, that's 7. And we want the average of the MPG of these cars. So we want the average of the MPG column, and that's going to be 28.4. 4b asks us to one by one delete the columns from this data set so that MPG, DISP, VS, and AM are the only columns remaining. All right, so this is a little bit tedious, but we can ask for the names of the data frame. Here are all our column names here, and we can just go one by one and null these out. So sub $, we want MPG, but we don't want CYL. We left arrow that to null. What that will do is it'll take away that column. Notice right now, here's what my preview of my data frame looks like. If I null out the cylinder column, that disappears. So I'm going to copy and paste this a few times. Which ones don't we want? Well, we want DISP. We don't want HP. We don't want DRAT. We don't want WT. We don't want QSEC. We do want VS. We do want AM. We don't want gear. We don't want carb. And we don't want KMPL. So null those out, and indeed we just have MPG, DISP, VS, and AM left. Now what we want to do is we want to sort this data frame on MPG from largest to smallest. Now, for whatever reason, sorting a data frame in R seems to be unnecessarily tedious, but this is what we do. So we type out the name of the data frame, and then we turn on the square brackets. And what we're going to do is manually order the rows of the data frame based on the desired sorting. So what we're going to do is use the command order inside the square brackets, put in the parentheses, because inside these parentheses we want to say what do we want to order by. In this case, we want to order by the MPG column, so we say sub $MPG. And then the second argument of order talks about how do we want this sorting to happen. Do we want decreasing equals true, in which case the biggest would be on top, and then as we go farther down in the data we get smaller values, or do we want decreasing false? Well, we want from largest to smallest, so we want decreasing equals true. All right, so that's our condition on the rows, so I'm going to put a comma right after this, because remember with the data frame, we need inside the square brackets a comma, something to the left, something to the right. So I've taken care of what I want the rows to be, ordered by MPG, to the left of the comma here. I don't need to put anything to the right of the comma because I want all the columns. So I'm leaving it blank so that by default it'll report back stuff about all the columns. I'll run this and I do see that yes, this is sorted from biggest to smallest. All right, part 5 wants us to rename the cylinder column of MT cars to actually be cylinder here. So right now, if I look at the names of MT cars, here's my vector of names. I see that CYL is the second of the elements here. So I could say a name's MT car $2, or bracket 2 here. So that is just CYL, and I'm just able to left arrow that into cylinder. So if I do this, now I see that names MT cars bracket 2 is cylinder, names MT cars, we got cylinder here, and then what we want to do is we want to figure out what the average value of something is. So what are we asked here? So determine the value of mean MT cars $cylinder equals 4, then explain in English what this represents. That's a good question. So we'll run this and we get 0.34375. What does this number tell us? Well, all right, we can investigate a little bit further by just printing to the screen, what are we taking the average of? So if I print this out, I get a bunch of trues and falses. So when we're taking the average of a bunch of trues and falses, we're taking the average of a bunch of zeros and ones. False is 0, true is 1. So we're calculating the proportion of elements in a vector for something. What are we actually checking here? Well, the logical condition inside those parentheses is cylinder double equal 4. So it's essentially looking at the fraction of elements in the cylinder column that are equal to 4. So for those of you watching, and for those of you thinking ahead to the midterm exam or the final exam, there's always a few questions about, all right, take this command and translate it into English. So this is a really good question that illustrates kind of what I'm going to be going for those exams. Translate that R code into English. Now, you won't be having R to kind of walk through it step by step, but this gives you a good idea of what I might be asking here. All right, part 3 is going to have us work with factor levels, renaming and combining factor levels. One thing that's super important to know how to do in business analytics, and something that's relatively tedious, unfortunately. So what we're going to do is we're going to work with the vector called random letters. So what's the contents of random letters? Let's just print the contents to the screen. All right, a bunch of random letters. It's a categorical variable. We see a levels vector associated with it. The levels vector is sorted alphabetically by default. So here are the possible values. The levels tell us what values are allowed, what values aren't allowed as values in that categorical variable. So how many of the 26 letters do not appear in random letters? We just chose at random the elements of this vector here. N levels lets us know how many levels a categorical variable has. So it has 24, so I could do 26 minus n levels. We know 2 are missing here. However, it says, although n levels quickly gives you the number of levels of a factor, try using a combination of length and levels. So n levels, that's a cute command to know, and it's a nice shortcut, but you might not actually know this here. All right, so how could we do this? Well, if we print out the levels of random letters, this gives us a vector of all the possible values that are allowed to be entries. That's basically what we see right here. So we could count up the number, length levels, and that would get us 24 as well. So we could do 26 minus that value. Now we want to figure out which of those two letters are missing. So we could scan through this vector and pick out which letters we don't see, but that's pretty tedious. We could imagine a situation where we had, say, 10,000 different levels, two of which we want to determine if, all right, is it in there, is it not in there? We wanted a better way to do this. Now, there's a command called setdiff, which is a very useful command for R. Setdiff x and y will let you know what elements are in the vector x, but that do not appear in the vector y. So if we run setdiff, what we'd like to know is, okay, well, what elements do we see in the letters vector? These are all the letters A through Z. What elements are in letters but are not in the levels of random letters? That'll let us know which two are missing here. So we don't see F, yep, and we don't see W, yep. So setdiff, really useful command kind of in very specific circumstances. All right, 6C wants us to get some practice renaming levels. And this is one of the more important things that you need to learn in business analytics when you're working with R, because very often you'll be combining levels together just to make the analysis go a little bit smoother. So rename the levels A, E, I, O, U to be vowel. How do we go about doing this? Well, let's do this the safe way. And here's what we'll do. First, I'm going to start out by printing out what the levels of random letters are. So we have the letters A through Z, but we're missing F and W. Now, the way that we change the levels is to type out levels of the categorical variable we want to change and then put in square brackets. And inside the square brackets, we know we put numbers to refer to the positions of the levels that we want to change. Now, in this case, we see that it's the first level, it's the fifth level, etc., that we want to change to be vowel. But we don't want to hard code 1, 5, etc., because it might be the case that later commands we end up running reorder the levels so that the first level is something else besides A. So the safe way uses the which command to automatically determine where inside the levels vector contain the elements that we want to be changing. So inside which, what we're going to do is once again have levels of random letters. That's the vector that we're diving into to see where we find certain elements. So which levels random letters, percentage in, where do we find A, E, I, O, or U? All right, so let's break this down. The percentage in says, all right, dive inside the vector to the left of percentage in and report back the positions where you find an element in the vector to the right-hand side of in. So in this case, if I ask, okay, which levels random letters percentage in this vector here, it'll say, well, the 1st, 5th, 8th, 14th, and 20th position are where I find one of these elements here, an A or an E or an I, etc. And we can confirm this by actually running this entirety. The command here, we do indeed find A, E, I, O, U. So we've made specific reference to these particular levels. And if we want to change them to something else, we can just left arrow and put in quotes what we want to change it to. So if we want to change that to vowel, boom, now all A, E, I, O, U has been changed to just vowel. Now we want to rename the level Y to be both, and I'm going to use the same sort of logic as I did up here. So I'm going to straight up copy and paste this. I know I'm going to be renaming it to both. And in this case, which levels am I interested in changing? Well, in this case, just the level Y here. So on the right-hand side of percentage in, my vector is only going to have one element in it. It's going to be the vector containing only Y. All right, so change the Y now to be both. So we see it's been replaced. And then what we're going to do is to rename the rest of the levels to be consonant. And there's a whole bunch of stuff here that talks about, all right, well, how do you change everything but a certain level to be something else? And in fact, this case, it's pretty useful to know this. Now we can use the same syntax here. We could say, okay, well, I want to change all the consonants to be the word consonant. But the consonants, that's a lot of stuff. That's the letters B, C, D, G, H, J. That's a lot of stuff that I don't want to be typing out. It's easier to say, all right, take everything but vowel and both and make that to be something else. So how do we end up doing this? Well, let's use what we have up here as a guide. This guide right here says, okay, here's my categorical variable x. I have a bunch of levels, A, B, blank, C, D, missing, and unknown. And the command here, I have a blank a few ways actually, with nothing in the middle between the two double quotes, with a space in the middle, double quotes. And what I want to be doing here is I want to be combining everything but levels A and B into a level called both or other. So how is this command set up here? Well, looks like the command we've already run here where we say levels x, then turn on square brackets, and then which levels x in, here's a vector of the everything we don't want to change here. So the only difference is actually this small exclamation point. This small exclamation point, just like what we saw in not equals, essentially negates the condition that we're specifying. So not equals is not equals. This is basically saying which levels are not in A or B. So if I run this part of the command here, notice that it is printing out everything but A and B. So we're renaming all of that to just other, and indeed we've successfully done that. So, okay, how do we do this here? Well, a lot of the syntax is similar to what we'd already run, so I'm going to borrow what we had done before. And I'm going to pay very close attention to where the exclamation point comes in, because I basically want to change everything except for both and vowel into consonant. So I just have to worry about where do I put that exclamation point. Well, it comes right after the which. However, I also need to add in an additional set of parentheses here. So a left parenthesis in front of levels, and I need to close that off on the right. So dive into the levels vector. Right now it contains this. Find all the ones that are not both and vowel, all those positions, and rename that to be consonant. And so now when we run table on random letters, I get my expected frequency table. All right, 6F says to repeat C, D, and E, but for a different vector. So here's my random letters. Now I have 500 different elements of this vector, pretty long vector here. And C, D, and E just wanted us to rename those levels accordingly. So if I take what I wrote for C, if I take what I wrote for D, and I took what I wrote for E, put it all together, I don't actually need to do any modification because the vector is named the exact same thing. Rename the vowels to be vowel, rename Y to be both, and rename everything except both and vowel to be consonant. So running these guys and then adding in frequency table tells me how many of each of those three levels I have. All right, part 4 wants us to work with a dirty data set. Now, this is data that's been handed to us from the development office, and I'm going to make sure that I'm in the right folder to read in this data file. So currently, if I type in getwd, it tells me that I'm in a folder called supply in my documents folder. That's not where this data file lives. This data file lives in my BAS474 folder. So I'm going to go to session, set working directory, and I'm going to choose the directory. I'm going to go to my BAS474, and in this case I have in my assignments and in my Practice1 F18, this is where the UT Alumni raw data frame lives. So I'm going to set the working directory to be that, and now if I run getwd, yeah, I'm in my 474 folder, specifically a subfolder that contains that data file. So I can read it in. It takes a few seconds because it's a big data file. And what we're going to start out with doing is printing to the screen the number of columns and rows in the data. So a few ways to get this. If I say dim That gets both of these. The first number is the rows, second number is the number of columns. I can see that information up here as well. And row of alumni tells me the number of rows specifically, and then col tells me the number of columns specifically. And it would help if I didn't typo that. And then also use head to print out the first few rows, specifically first 3. Head data frame, comma 3 will print out those first 3. And we're being asked to spot some of the data integrity issues. So just scanning through, here's some stuff that we see. So number 1, inconsistent format for zip code. Some have those additional 4 numbers, others don't. So we got inconsistent zip code format. Notice we have some columns that have a lot of blanks in it. So job title, city 1, these are all blanks here, just empty spaces. Blanks for many columns. For example, job title. Put little back quotes around that, so print it out just like what R does. We see missing values too. We see NAs, grad date, and even campus, all this stuff. We see some blanks, lots of NAs. Weird symbols here, kind of a whole bunch of \T's here. Weird symbols in non-UT degrees. More weird symbols. Dollar signs have crept in instead of actual numbers. Dollar signs and periods. It's stuff that should be numeric. And we have some row columns here. What's x, x.1, x.2, x.3? Everything else has a nice name associated with it. So maybe these are erroneous columns, x, x1, etc. So like most things in business analytics, the data that's been handed to you, it's going to have some issues. You're going to have to spend some time cleaning it up. So 7b asks us to get rid of these erroneous columns, nulling out columns that we know we're not going to actually be analyzing. So the very first column, actually ID number, that's just an identification number. That's not going to tell us anything interesting about the alumni here donating. So we can null that column out along with the other erroneous columns. So if we left arrow it to null, we'll see that that first column here, ID number, boom, it's gone. And then we can do the same thing with these other columns, x, x.1, x.2, x.3, and then finally x.4. Get rid of those columns. We don't need them. Null them out. Makes our data set a little bit smaller, which is nice. You see they've disappeared there from the end. All right, so we also spotted that monetary amounts had the dollar signs and had the periods in them, and even commas too, if it was bigger than 1,000. Now, if we want to convert these into numbers, we need to be a little bit clever about it. So, and it'd probably be easier to go back to the original Excel file and just remove that sort of formatting. But it's a good place to introduce the gsub command, which is useful for text processing. So as an example, here's a vector x. It contains text entries, and we see some weird characters, dollar signs, periods, exclamation points, etc. Gsub lets you go into a bunch of text expressions and replace certain characters by others. So the first argument tells you what you want to replace, the second tells you what you want to replace it with, and the third argument tells you the vector containing that text that you're going to be doing that replacement. So this first one right here goes through each element of the vector x and replaces lowercase e by uppercase e. And you can get fancy with it. If you wanted to replace the string double L with 789, no problem. You can go and do that, and that hello becomes HE7890. There's some cool syntax things that you can do with gsub here. The square bracket says, okay, every time you see any vowel here, anything inside the square brackets, replace that with blank. So we see all the basically vowels have been stripped out here. Blank with nothing in the middle is no character at all. Bracket bracket colon alpha says anything that's a letter, replace that with whatever the second argument is, the @ symbol here. And so there's a bunch of other symbols. ALUMNI does numbers and letters. Looks like we're replacing those with a star. And then bracket bracket colon PUNCT, punctuation, replaces all punctuation marks, exclamation, @ symbols, dollar signs, etc., with blank. So here we stripped out dollar signs, we've stripped out periods, we've stripped out exclamation points here. So we can actually strip out these dollar signs, these commas, and these periods with that punctuation shortcut. And let's actually go ahead and do that. All right, so one by one, tedious. Data processing, data cleaning, always going to be tedious. One by one, we're going to strip out those punctuation marks and convert these columns into numeric. Now, in this case, the example that I'm showing does it the old-fashioned way, where we literally refer to the comma, we literally refer to the dollar sign, which takes special treatment. It's 2 backslashes to have it actually be treated as a dollar sign, because normally dollar sign turns on column reference. So here, this is actually taking the values inside the LTG2UT column and strips out the dollar signs and commas manually. And then as.numeric forces that from text to actually be a number. So we could do it this way, or my favorite way. Or in this case, it's actually better to do it this way, because if we do it the punctuation way, let's just see what happens. So if we use the punctuation shortcut, notice what will happen is that now all of a sudden these amounts look super huge, because what it did is it took away those decimal points and took whatever the result was and treated that as a number. So we basically upped everyone's donation amount by a factor of 100. Now, the development office would love if that happened, but we want to be faithful to what the data actually says. So we don't actually want to do this punctuation shortcut, because that gets rid of the decimal points that changes what the numbers actually refer to. So basically what we do is we stick with the example that we're given us. In square brackets, we give it a list of characters that we want to be changing. And in this case, we want to change the character dollar sign, which we have to represent as \\$ dollar sign. And then also comma, replace those with blanks. It'll overwrite the LTG2UT values with the numeric equivalent, and it wants us to do this manually for every single one of the offending columns. This is what I mean by tedious here. So luckily we have a list of names, so we can just kind of copy and paste and be very, very careful about doing all that copying and pasting appropriately, making sure that we're not skipping over any, making sure we get the left and the right hand sides appropriately. We'll actually learn shortly in Units 3, when we talk about for loops, how to do this efficiently instead of having a line of code do this all one by one, writing one line of code that's just going to loop through all of the columns that we want to change and process these columns automatically. A lot more fun than this tedious copying and pasting. Every time I copy and paste, I leave myself open to having made a mistake, and it's really easy for a mistake to creep in when you do a lot of stuff like this. But here we go. Let's kind of assume that we have all those columns done correctly, kind of scan through here, and if we look at these money amounts, we see that, okay, there are numerics, numerics, numerics across the board here, so it looks like we've done our job. All right, print to the screen the average and the median amounts of this column right here. Well, to get the average, we use the mean command. What are we taking the average of? Well, this particular column of the data frame. So alumni dollar sign turns on the column reference, dollar sign this gives us the average, and then the median amounts, I can just change the name of my function to median. So at least half the people actually didn't donate in the fiscal year 2015. The median tells us kind of the midpoint of all those values. Half the values are smaller, half the values are bigger. So we have half the values being 0 or smaller. You can't donate negative, so that means that at least half of those are zeros. All right, question 9 asks us to tackle the degree 1 grad date format, which is an unusual format because it looks like the first 4 characters tell us the graduation year, and the last 4 tell us something about the graduation month. So just printing out the first few entries of degree 1 grad year, or grad date. Yeah, weird format. And we have NAs here. So some illustrative code for how we can just get out those first 4 characters, the graduation year, we can basically divide by 10,000 and then take the floor. The floor rounds down to the nearest integer, so we would get 1970 out. Now, it turns out that, okay, well, if we were to scale that up by a factor of 10,000, multiply that by 10,000, and take the difference between what we see in that field and this value here, that's actually going to tell us something about that graduation month. So what we're going to do is we're going to add in a new column called degree 1 grad year. How do we add in a new column? Name of the data frame, $, name of the column we want to add, and left arrow that to be the values that we want to place in that column. So what we're going to do is we're going to take the floor of the degree 1 grad date divided by 10,000. Kind of our trick to extract out just those graduation years. Left arrow that into grad year. And then we're going to do this for month as well. So degree 1 grad month. We'll just borrow this formula up here and take the original value, subtract off 10,000 times the floor of taking those original values divided by 10,000. All right, now in this case, we actually wanted this to be a categorical variable. Here, the two columns that we just added just contain numbers, as we can see through here. Now, to make these categorical variables, then we need to make sure to put factor around these values. So don't treat this as a number, treat this as a categorical vector. Let's actually put that inside the factor function to make these be categorical variables. So there we go. All right, so we're going to run summary on our newly created month column and take a look. All right, so got a bunch of weirdness. So we see a lot of entries that are 600, a lot of entries that are 300, a lot of entries that are 1200, and then some weird entries. What does 822 refer to? What does 607, 1219 refer to? This is always going to happen with real-world data. You'll have values that you don't really know what they correspond to. This is where that domain knowledge becomes important to figure out what these values are supposed to represent. Should this 607 really be a 600? Should we replace that with a missing value? What exactly should we be doing with these? So it's kind of weird stuff, but we have some guidance over what I want you to do at least with the values we see in here. All right, so what we're going to do is rename 300 to be winter, 600 to be spring, 800 to be summer, and 1200 to be fall. All other levels are going to be renamed unknown, and we'll do this the safe way. All right, so how do we change the levels of a categorical variable? Well, let's start out by just printing out what the levels of this categorical variable is. So here's our vector of levels. And what we want to do is, let's start out by changing the 300 to be winter. We want to change the second level in this vector to be winter. Now, the dangerous way is to put on a square bracket 2 to refer to that position specifically, that 300, and to left arrow that to be winter. This is the dangerous way because what if those levels get rearranged? What if I have them in a different order? Then square bracket 2 might refer to something else. So we don't actually want to do it this way. Instead, what we're going to do is we're going to use the which command to automatically figure out where inside the levels vector contains that 300 that I want to change. So inside the square brackets, after levels, I'm going to say which levels degree 1 grad month double equals 300. So right now, if I just run that which command, it's going to report back 2 because 300 is the second element of this. But I want to make sure to specify where inside that levels vector contains the element that I'm changing with which, just in case those levels get reordered. It'll always find it this way. All right, and in fact, what I'm going to do, because a more general thing is combining multiple levels together, instead of double equals, which restricts myself to only changing one level at a time, I'm going to do %in, and then just make this 300 a text vector here. So this way, I'm still going to replace 300 with winter, but in case I wanted to combine multiple levels, I could actually have a vector containing the names of all the levels that I wanted to combine together here. So, all right, let's make that change. Dive inside the levels vector, figure out which was equal to 300, and we'll change that level to winter. You'll notice now if I look to see what those levels are, I see that instead of 300, I see winter. So my base code is here. I just need to copy and paste this a few times because we're going to be changing 600 to be spring. We're going to be changing 800 to be summer, 1200 to be fall, and we want all other levels to be something else. All right, so run these commands. I'll look to see what the levels are. All right, and I want everything but this level to be unknown. All right, so there's a nice way of doing everything but. We covered this earlier on in this exercise, but here's a quick review. To do everything but a set of levels, because it's a little bit too tedious to type out 0, 318, 511, 512. No one's got time to do that. What we're going to do is we're going to borrow this line of code right here. I know I'm going to be left arrowing something to be unknown. And instead of typing out here the vector 0, 318, all in text or whatever, what I'm going to do is I'm going to very carefully put an exclamation point right after the which and add in an additional left parenthesis. And I'm going to close that off by adding an additional right parenthesis over here. And I'm going to say I want everything but winter, spring, fall, and summer to be unknown. So to do everything but, that required the exclamation point, and it requires me to specify everything I don't want to have changed. So I don't want to change winter, I don't want to change spring, I don't want to change summer, and I don't want to change fall. Long command at this point, but let's read it. So right now the levels vector contains these values. I want to change everything but winter, spring, summer, and fall to be unknown. So inside the square brackets in the which command, by putting in the negation symbol, the exclamation point, and then giving it a vector of values that I don't want to have changed, well, if I just run this part of the command, it lets me know I want to change that first level, the third level, the fourth level, etc., all of these levels to be unknown. So we've got that. Printing out the levels command now. Here's what we have. And if we now ask for a summary, that matches up. So it takes a bit of practice, renaming, combining levels, everything but. Definitely always refer back to that Introduction to R Programming PDF that I posted up on Canvas, or follow some of the hints that you find in the assignments. The hardest part when it comes to data processing, I think, is combining levels, combining everything but a certain set of levels, etc. All right, 9C wants us to null out this grad date column. It's no longer necessary. We've handled it, so we can get rid of it here. All right, question 10 wants us to deal with the city column, because unfortunately city is somewhat ambiguous because a lot of cities appear in multiple states. We have a city and a state code column here. Franklin, almost every single state in the union has a Franklin somewhere. And so what we're going to do is we're going to create a field that combines the information in the city and the state columns. So how are we going to do this? Well, we're going to use the paste command. Small example, if I define the vectors x and y to be as follows, I could create a new vector that combines the first elements of x and y, the second elements of x and y, etc. If I do paste x comma y, notice what ends up happening. I get a vector of length 3. The first element are essentially the first elements of those two vectors pasted together. By default, it's going to put a space between those two elements. If I want to have something else, I can specify, all right, separate those two by something else here. In this case, I'm giving it a double quotes with nothing in the middle, so separate them by a blank. So now Springfield and Illinois, not separated by anything whatsoever. So what we're going to do now is to create a column called location. So alumni $location, creating a new column that way. It's going to be a categorical variable, a factor. So I need to make sure to use the factor command and put something inside the parentheses to give it something to work with. It's going to be obtained by pasting together entries in the city column and the state columns. So we're going to use the alumni $city and alumni state code, pasting these two things together with nothing in the middle. So if I just run that paste command, I see, all right, I got Knoxville, Tennessee, Oak Ridge, Tennessee, Norcross, Georgia, etc. By putting that inside factor, this makes it a categorical variable. Here are all the entries, and it's keeping track of a list of levels here. And we're left throwing that into a new column called location. All right, so we can check to see that there's 979 Franklins in, let's see, oh, that was from before. So 979 Franklins. We could look to see, well, how many Franklin, Tennessees are there? So how many entries in the location column do I find Franklin, Tennessee? Well, almost all those Franklins actually belong to Tennessee in this case. All right, once we've done this, we can null out the city, null out the state code column, because at this point it's redundant information. We've handled those two columns appropriately, and so we're good to move on. All right, so if we look at the first few levels of this location column, the levels are the possible values, we see issues. We see a blank but represented by a few spaces. We see a blank TT. We might want to get rid of those or just rename them to be unknown. We don't know what they really correspond to. So in this case, we're going to recode the first three levels of the location column to have the name unknown. All right, well, how do we do this? We're combining some levels together. So we're going to take the levels of alumni $location, which currently is all of these levels, a lot of them, 3,220 different levels. And in this case, I'm going to do this the dangerous way, or show you the dangerous way first. So we said that the first three entries here, this blank, blank with spaces, and space T, is the ones we want to change. So let's do this the safe way, however. I could do this to say, all right, let's make this to be unknown. But in the case this gets reordered, the first three might refer to something else. I might want to do this the safe way. All right, so we're not doing this the dangerous way where we hard code the positions of the levels vector that we want to change because things might get reordered. So what do we do instead? Well, we use the which command here. We're going to say levels alumni $location, and then we'll automatically figure out where those positions are by asking which alumni levels alumni $location are somewhere inside a vector of values that we want to change. So what are the values we want to change? Well, it's very often easiest to just copy and paste these levels from the output of the levels command itself so that you can make sure to get all of the characters that are in there that might be somewhat hidden. So we can look to see which levels are inside this vector here. Well, the first, second, and third. Great. So we want to take these levels and we want to rename them to be something. So we want to change this to be unknown. And once we have that, then we can say look at a table of location and get a frequency table of all the locations. Now there's so many here that we're not going to be able to find the number for unknown. So we might ask, all right, well, length which alumni $location is equal to unknown. That's a good way for counting up the number of times you see a particular value in a vector. So it looks like 673 unknowns here. Question 11 talks about the city.1 column. Well, that tells us the city in which the alumni is currently employed if it is known, and has a very low information density here. So one thing we might want to do is investigate this column and determine whether or not we even need it here. So the first thing that it asks us is how is a missing value or blank represented in the column. So let's just look at the head of the levels vector of this and just take a look. So it looks like a blank is, or a missing value is just a blank, pair of double quotes with nothing in there. So it is just a single space or nothing at all, really. So a missing value is a blank. In other words, a pair of double quotes with nothing in the middle. And it's asking us to recode the levels of this column, so that it's either known or unknown. Okay, so blank is unknown. Everything but that is going to be known. So we're going to borrow what we had put up here when recoding and combining levels. So what we want to do is we're looking at something about this city 1 column here. 111 levels, we basically want the first level to be unknown and the rest of them to be known. So we'll do this the safe way. So using that which command once again, we can have it automatically dive into this levels vector and determine where we find those blanks. So the blank is the pair double quotes with nothing in there. If we run just the which command, we'll see that it spits back out the number 1 here. And so indeed, we want to take this level and rename it to be unknown. So we can do this, and once we do this, we can print out the levels again, and we see that unknown has been replaced, or that blank has been replaced by unknown. Now we want to do everything but this level to be something else. So we could go through and methodically, in this vector right here, put in every single name that we want to change, but we'll use the everything but shortcut. So how does this work? Well, the syntax looks very similar to what we just had here. If we want to do everything but a blank, though, we just have to put in exclamation point right after the which, add in a right parenthesis, get rid of the one that's automatically put there by R, and close that off over here. So which levels are not blank, just running that which command, well actually, which of them are not unknown? They're all not blank now because we just changed the blank to unknown. Which are not the level unknown? Well, notice it's everything but the number 1 here. So everything but unknown is being returned by this, and we want this to be known. So there we go. Now we can make a table of this just to see what some of these results look like. Now it looks like we only know 656, and we don't know the vast majority. But we recoded this very quickly into one of 2 values here instead of dealing with all this stuff separately. A lot of these cities only appeared once. We might as well just treat them as either we know something about it, we don't know something about it. All right, now we want to rename this column to be city employed because city.1 isn't very informative. We'll say names alumni. Which one was city.1? Well, that's kind of hard to tell. The nice thing is, I don't have to refer to it by number because I know, well, let's see if this works. No, it doesn't work. We can use that which command once again. Which names alumni equals to city1. I don't know where it is in this vector of names here. It looks like it's the 6th element. Is that true? Yeah, that's city1. So let's rename this to be city employed. All right, 12th and final question asked us to analyze the lifetime gift to University of Tennessee. That's how much money the alumnus has donated to UT so far. So what we're going to do is we're going to make a histogram of the values inside LTG to UT. Now, you've already converted this into numbers earlier on, so we can make a histogram of the values. Now, we see that this is a completely useless histogram. All the information is compressed inside the single bar because there's one alumnus who's donated a lot of money to the University of Tennessee. I'll let you guess who that person is. You probably know them. But this histogram is not useful. In analytics, it's pretty rare that we actually want to analyze the values as collected. Very often, we're going to want to analyze a transformation of them, and very often the logarithms of the values. So let's explore the logarithmic transformation. If we look at a summary of the lifetime gifts to University of Tennessee, I see that a lot of people haven't given yet. The median is 0, so that means at least 50% of the alumni haven't actually given anything to UT yet. Some just graduated last year, so no big deal. Now, the problem with this is that we can't take logarithms of 0. So we need to do a trick. Usually a good trick is to add to every single value that you're trying to take the logs of some number. And the number you're going to want to pick out is whatever number to make the smallest value equal to 1. Typically that's the guideline. And in this case, since the smallest number is 0, why don't we add 1 to everything before taking the logs? Okay, that sounds like a pretty good idea. So if I do hist of log 10 of 1 plus the value I find in that column, I get much more structure here. Here are all the people who's probably not donated yet. The log of 1 is 0, so these probably represent all the zeros. But here's a much more accurate kind of glimpse of what the distribution looks like. Since we're on the log scale, 2 represents 100, 4 represents 10,000, 10 raised to this power here. And so here we go. For 12a, we're creating a vector called log LTG to UT. It's going to be the log base 10 of the numbers in that column after adding 1 to it. And then we're making a histogram of this vector that we've created. It's outside the data frame. I didn't add it as a column. And we're looking at a summary of the values here. All right, so the average value is just this 1.099, which I could also get out by just asking what the mean is of these values to get a few more decimal places. And what we're going to do is we're going to untransform this value. So on a log scale, it's just about 1.1, but you're never going to report to your boss, hey, you know, the average of the logarithms of the amounts donated is 1.1. No one's going to know what that corresponds to. We'd like to know, what does that 1.1 correspond to back on the original scale? All right, so because we defined the logarithm of LTG as actually the log 10 of 1 plus those values, in our transformation, to unlog it, we're going to take 10 and raise it to this value that we see here, and then add 1 to that, or subtract 1 from that amount. So that's how we unlog this transformation. Because we added 1 to everything, we got to subtract 1 from the result here. So let's take 10, raise that to the mean of log LTG to UT, subtract 1 off, and there's our answer. So about $11.56. That looks to be a pretty good summary for the typical donation amount so far. And there we have it, all of Practice Set 1 in the nitty-gritty details.